transform ADC values to DQ values and those kind of things. Uh, Tuesday, next Tuesday, I'm gonna go 40 minutes over the time, and we'll get a break and we'll go, because we missed one class, I have to go make up for that one. And also I bring some simulation, I show you the TDQ transformation, because in the first phase one of the project, you were not involved with the DQ and those kind of things. Today I'll finish, hopefully the control, I wanted to be part of this say, and next Tuesday, I'm going to teach you another method for science. PWM switching, it's called the space vector, naturally sampled space vector PWM. This is the simplest space vector PWM method, which is more efficient. I'll tell you what's better about that compared to sine PWM. And after that, I run a few cases on the DQ and those kind of concepts. We talked about it. I said when you are in the DQ, you don't have to deal with those variations like 60 Hz frequency and those kind of things. You can get a better feeling about what you are doing with the DQ transformation and those kind of things. And I'll hand you the second phase of the project. I'll work on it this weekend. I'll make it ready and I may send it over the weekend. I try to send it over the weekend, And the second homework also, I'll work on that one and give you. The second phase is not going to be that much of work, I'll give you, because already you have the base of the project for the first phase. Instead of being like a 6-step inverter, I want to make it, PWM inverter. Now you can see the again the harmonic spectrum, maybe similar things we did for this project, but with the PWM switching. To see how much your current waveforms are going to get better, how much your harmonics is going to get better. Basically, you become familiar with the PWM concept and those kind of things. And the major part of the project is going to be phase 3. Phase 3, I'll see how much time I'm going to give you. But I try to hand you in the phase 3 maybe the weekend after, so you will have like 2 weeks, 3 weeks to spend on that one. And the last phase for now is the solar. And right after the controls, I'm going to cover the solar. So if you guys will be ready, this week is a bit, what will be 4? So week 5. And hopefully by week 6, you have everything, for the project. And you have time until end of the quarter to go over it and finish it, phase 3 and phase 4. By week 6, so we have time to go over everything. This one will be the steps. Now, Arno is working on developing some simulation lab. This is about the DC to DC converters. After we are done with the solar maximum power and a little bit about the solar panels, I'm going to move on to the DC to DC converters, but not the circuits. Circuits you know about them. You know already about bar, boost, flyback, those kind of things. You want to work on the control of the circuits, as a voltage regulator, or maybe as a current regulator, these are the case. I ask him to prepare 3 labs for you guys, This is like, these are not very difficult, but you go build the circuit, you build the control group. Initially, you don't have to do the analysis, how to make it, stable. You can do it by try and error, ask help from Arnold to help you on that one. And you see how you can control a DC to DC converter, like a power supply you have in the lab, and those kind of things. And at the very end would be your final exam and presentation. Presentation will be about 20 minutes, something like that. So homework 2 and phase 2 project is going to come this weekend. Now, let's go after go back where we were. The last thing I finished, if you remember, we said in a 3-phase, in a DQ system, P is going to be 3 over 2 VDIV plus VQ IQ. And Q is 3 over 2 VQ minus VDIQ. This is what I proved this one, right? We went through it. How we did it is a P is VA, VB, VC times IA, IB, IC. I use the transformer function, and went through everything. And we finally get this equation. And we say VOIO, the 0 component, is 0. So basically that, because there is a plus VOIO here in the parentheses, I'm going to say in the balance system, that one is 0. You don't have to worry about that part. And after that, I said, if you select your axis is such that the voltage is aligned with the, I'm not sure which axis, with the Q axis. we said if we select this is the Q axis, right, and this is the D axis. Remember we said we have a V here, I here, right? And we call this one CV and we call this one CI, right? Here we said, we went through this, you wrote this one already. We said, okay, if we select this axis is arbitrary. Remember there was a delta. There was the initial angle, right? I can go rotate this one, the Q axis, to match my voltage. They will be in the same axis, in the same direction. If I select that one, I have my voltage like this, and for example, my current like this, or here, this way, doesn't matter. It's either leading or lagging, doesn't matter. It's both. So basically here, phi V is equal to how much? 0, right? Because phi V was the phase between the V and Q axis, if you remember, we look at your notes. So this one is 0, only we have phi I, which in this case is going to be phi, right? And this guy, actually this is a phi I, and phi is minus phi I, right? Because phi is a phi V minus phi I, right? So this is a leading case. Now if we have this one, what was the result of this one? If you look at here, if I project this one on the Q axis, how much is the VQ? VQ is how much? V. And how much is the VD? 0, right? So basically we place these two values in this equation, right? And V is the maximum phase voltage. What does it mean by say? I say maximum phase voltage. Let's say we have a 480 volt system, right? I have a three-phase system. We say this system is a 480 volt. What does it mean 480 volt? Line to line. If I have a three-phase system, when they give you a voltage, by default, this voltage is the RMS value line to line, right? This is what we learned from energy conversion. This one is going to be line to line, RMS value. By the way, next year, academic calendar year, we are going to start with power system analysis instead of energy conversion. And the three-phase and transformer will be moved. It's going to move to the power system. For those who maybe they had energy conversion and they're going to take that one, maybe the first 2-3 weeks is similar, but transformer is going to include the three-phase transformer and a little bit more power system oriented. It's a little bit different from just basically have from that. But from the energy conversion, we said if you have a three-phase system, a given voltage means line to line RMS, right? So if they say, honestly, what does it mean? This maximum phase voltage. When I say maximum phase, this is a three-phase system. We had a three-phase system, right? All the equation we went through, three-phase inverter connected to the three-phase grid. Now, how much is the RMS voltage of the phase? So it's going to be basically 480 over the square root of 3, right? That's this is the line voltage. Phase voltage is divided by square root of 3, right? And so this is the RMS. How much is the maximum of this one? Basically, this value later on you need it for control is this much. If it's a 480 volt. If it's a 208, it's going to be 208, right? You have a 480 system, you have a 208 system. Basically, whatever you have, you use this one, right? Now, so we said, okay, if we select the axes like this, we are going to have active and reactive power is going to be 3 over 2. VD is going to be 0, right? It's going to be VQ, IQ. VQ is how much? Is a V, right? And another thing that I'm saying here, see? V is a grid voltage, right? This is a grid type inverter. This is the inverter connected to the grid. V is constant. Voltage of the grid is going to change a little bit, but usually it's a constant voltage. For example, if we have 480, I know my V is this much, right? So one parameter is gone. I don't two parameters, VD and VQ, they are gone. So I have one constant number. It's going to make it easier. And how much is the Q? Q is going to be 3 over 2. I'm not sure if I'm making a mistake, but I think I had a negative here. Am I right? There was a negative. Where did I make a mistake in the negative one? Let me see. Minus VQI up here. Yeah, let's start from here. Minus VQI. This is this one. Let's start from here. So here it's going to be minus 3 over 2v IV, right? Now we are going to go to the control. So how we are going to control the system? Let me put a picture of the system, what we have. In this case, we are going to start with the battery. Battery is the easier case. Now I have a battery here. I'm going to put the block diagram, control block diagram of the system. This is my inverter. I can say DC, AC. This is my VDC, right? This is a DC bus. This is a battery. IDC. Actually, IDC can go this way or can go back. You know, you can charge the inverter, you can charge the battery, or you can discharge. But now I showed it this way, sending the power to the grid. Now we have a filter. I'm not going to put capacitor because it's going to make it more complicated with the equation. Just a simple, inductive filter, and we are going to ignore the R part. This R is the resistance of the inductor. Usually it's very small, but right now I put it here. And this inverter is connected to a three-phase grid. I call this one R, L, R, L, R, L. But usually they start with RA, RB, RC, but when the system is balanced, you're not going to design an inductor. They have 3 different R values, 3 different L values. They're all going to be the same. This is something we designed. We designed it balanced, you know what I'm saying? But if somehow you're not feeling good and you design an inverter, for example, phase 1 is 2 millihenry, phase B is 8 millihenry, phase C is, for example, 10 millihenry, so that's something wrong with you, not your own balance in the system, Because usually, this is under your control. You design a balanced inverter, a balanced inductor.
Is there any reason why we want an unstable system?
Unstable?
That's unbalanced.
No. We try to avoid that one as much as we can. As much as we can, Even if there is an unbalance, somehow we try to inject some signals to balance the system. We don't want an unbalanced system. We don't want it. R and L. And this one is the phase B, IB, IC. I call this voltage here EA, EB, EC. Now, before to get into the more math, after here we're going to go through lots of matrix calculation and those kind of things. But before going down, let me go with the easy version of this inverter control. What's the goal for us? We have a battery connected to the grid. What's the goal? Let's figure out first of all what's the goal, and we start to work on how to get there.
Charging.
So one case is charging the battery. Yes. Another.
Discharging battery.
Discharging the battery. So what does it mean that? Charging, discharging battery.
Power flow.
Current flow.
Power flow, yeah, or current flow, but power flow. You want to control the power going this way either or that way, right? But you want to control both of them, P and Q, right? You have an active power and reactive power, right? You want to control both these two. For example, I want to charge my battery with 2 kilowatts. I want to charge my battery with 5 kilowatts, right? So this is what I want to be able to control that, to say, hey, go with this much power charging. Go with this much, current charging. Power and current, they're the same. Why? See, power and current, they're the same. Because it's a constant number, right? For example, let's say 5 kilowatt means, for example, 10 amps. 10 kilowatt means 20 amps, right? And Q is related to what? Go back to the power triangle. I'm going to use it here. If you go back to the power triangle, this is the P, this is Q, this is S, this is Phi, right? Huh?
Q is reactive power.
Q, what I can do with Q?
Minimize speed.
If I make this Q 0, S is going to be, I'm not going to make it perfectly 0, but I'm going to say this. This is my S, right? What is going to happen?
You have the maximum amount.
phi is going to become 0, right? Going towards 0. Or cosine of phi is going to be 1. They call it unity power factor, right? We want, those one, again, they had energy conversion. One section we're talking about, it was about the power factor correction, right? Power factor correction basically was, hey, let's reduce Q. I don't want to explain why we want to reduce Q, but basically we're trying to reduce the Q consumption, right? So basically, I want to charge my battery with whatever power I want. In this course, we're going to go with this one. Under how much Q?
0.
0, because it's going to give me unity power factor, right? But there are some devices. They call it SVC, static var compensator. They are designed to inject Q or absorb Q. There is no power. P is 0 for those ones. They call them a static var compensator. On that one, they are different. We use them for power factor correction, and we use them for voltage support. But in this course, we want to keep it unity power factor. Unity power factor means Q 0, right? Q 0, right? So Q 0 means ID 0, right? Now, what we are going to do here, we are going to do this one. We are going to, in the real system, we are going to go sense. We are going to put a current sensor here in the system. You don't need 3, 2 is enough, but here I'm going to put 3. So far I'm not spending any money, I'll go with 3. But usually this is the cost reduction. You can do it only with 2 current sensors, So these 3 that are coming here, we don't need a VDC in this case, but I'm going to sense the VDC also. I'll use this one. And I'm going to have a box here. This is my controller. It could be a DSP, it could be something else. DSP, control board, microcontroller, or whatever. They call this one power section. You're working with battery, grid, inductor, inverter, all those, bulky part, right? They call this one control part, right? Usually you sense the current. Here I'm not sensing the voltage, but you can sense the voltage also to bring it here. We need a voltage, so let's put it here. But we're not going to talk about PLL, You bring VABC. I mean, you can bring a VA, VB, VC. Then I'm saying VABC. And in this course, we do care about this one more. Because we're not going to work on the PLL, so we don't need a VABC. IA, IB, IC, they're coming here in my control box, right? And VDC also, we are not going to use it, but for the solar power, solar maximum power point, we need to get the VDC. VDC and IDC, both. VDC and IDC. These are the ones that will come here to my DSP. VDC, IDC. Now, at the end of the day, what this controller is going to do? What?
Open switches at the right time?
No. This controller, what it's going to do, is going to send 6 signals SA plus to SC minus. SA plus, SA minus, SC plus, SC minus, SC plus, SC minus. These are the switching functions, you know what I'm saying? There is the one I showed it on the board, I said, okay, for example, with the sine PWM, I'm going to have this control waveform, right? I cross it with this one and compare it. I said, okay, on, off. Those on, off, they're going to come here. And usually these inverters, they have one interface board here, they call it gate drive. This control signal, they go to another board. I'll bring one inverter maybe next week, here you can see all these things. All these signals, they go to the gate driver, and the gate driver is going to change this control signal to power signal, right? And then connect it to the IGBTs, and start to turn on, turn off the switches. In PC also, even if you look at it, when you do this kind of thing, when you have a switch, if you go to check the PC, for example, when you have a switch, right? this is the gate drive, right? This is the gate signal, right? This is the gate of that IGBT. It forces you to use something like this, to send the gate signal here. You have the kind of math things, calculation. If you don't put this one, it's gonna send you an error. This is like a gate driver between the control signal and the power signal. You know what I'm saying? Convert the control signal to power signal to be able to switch the inverter. And this controller usually is a DSP, digital signal processor. It could be TI-28335, TI-2812. There is an analog device. There are tons of DSPs, but TI-335 is a very good one. I recommend you guys, if you can learn the programming of that processor, is really good. It's very good for finding a job. If you guys can program, DSP is a really, really good job, to be able to, and you can get a good, job in the future. Good for those that are interested to work in this field. Now, so we have the power circuit, right? We want to control the P and Q here. That's the goal here, right? We want to do the active and reactive power control. And we know what we are sensing. I'm not going to use these two, as I said, and this VABC for this phase. This one, we need somebody ask, Nam, I think asked, about the, in phase one, when I say 90-degree shifting right or left, basically, you need to know where is this phase, right? When you have a grid, for example, I don't know what's the phase. There is another piece of code, they call it PLL, phase lock loop. You put that one, it's going to tell you what's the phase of this grid, at any moment. Now, you can either shift this way, or because when you know where you are, it's very good grid, either you can shift it this way and say, okay, I want to be here, or I want to be here. But in the project, I don't expect you guys to do that one. It's just manual. You say, I know you set the grid phase, 0, and you say 90 degree, you can make the control minus 90 manually or plus 90. But this thing has to happen automatically in the system. And you need to have a PLL. This block here, the guy here, this VABC is going to come to a block they call PLL, and this one is going to give me theta. Theta, right? This is the only time we're talking about this one. I'm not going to tell you what's happening inside this PLL. But we're going to have this theta here. Remember all this transformation, we had sine theta, cosine theta, those things. The theta is coming from here. The PLL is going to give us the theta. But I'll show you to make a fake PLL. You guys know how to make a fake PLL and use that one. Now, we want to control active reactive power. We sense the current, voltage, DC, AC, all those things we need. Now, and send all the signal to the controller. All the math is going to happen here. Do all the calculation it needs, and at the end, it's okay, hey, you turn on here, you turn off here, you turn on here, you turn off here, and send it to the inverter, right? Let's see how it's going to happen. So, we said we are going to control the power, right? Let's say call it P star, or P ref. Let's just call it P ref. This is what I want to have, right? 10 kilowatt, 5 kilowatt, whatever. We said how much power we want to have, right? P ref. How much is the P ref? 3/2 V IQ ref, right? Or I can say IQ ref is 2 P ref over 3V, right? Correct? How about Q ref? Q ref, we will set it, 0, but let's say if you want to control the Q also, in this case, we want to say it's 0. But sometimes you want to control the Q. As I said, the new solar installation, they're all working with the unit power factor right now. But for very soon, the utility company, they're asking, hey, you should do some reactive power support. Plus 0.8 minus 0.8. The power factor shouldn't be perfectly, 1. I want you to go either 0.8 leading or 0.28 lagging. I think you should cover that one. Basically, you have to change Q ref, right? If you change the Q ref, you can go either this way or you can go this way, right? So this is the phi, and you can see cosine of phi is going to be either positive or negative, right? Leading, lagging. But as I say, in this course, we are going to say it's 0, no Q ref. The block diagram I'm going to put it together is going to be general block diagram. You can use it for reactive power control. But later on, I'll tell you to set the Q ref 0. And it's going to be 3/2 So basically ID ref
How come I used the negative?
Oh, there was negative, yeah, whatever. Yeah, we don't say negative. So now I have this one. I'm going to put the blood diagram together here. I'm going to bring my PREF, my QREF. See, this one is all happening inside this box, right? This is the controller. I have a box here, a math box. It's going to get V as an input. How we are going to calculate V? This PLL is going to give you theta and V both. Basically. Theta and V. Both they are going to come from the PLL. It's going to measure the voltage and phase online. Even if the grid voltage changes a little bit, this guy is going to tell us how much. But as I said, forget how it's going to calculate. If we assume the grid is fixed, and you can calculate V based on what I put here. 480 divided by the square root of 3 times the square root of 2, right? That's what we have. Now, basically this two equation is going to be built in here. If you know how much is your PREF, how much is your QREF, right? Use this equation and V, you're going to calculate IQREF, and IDREF. Now, so basically to control the peak active and reactive power, I have to control the current, right? Now, these are the reference values I want to have, right? I want my current to get to this value. But in the real circuit, right, in this circuit, I have some IA, IB, IC, which I can transform them to DQ, I get the ID, IQ actual, right? They may be different from the reference value, right? This is a control loop. I'll bring the minus here and minus here. This is the ABC to DQ. This is the C matrix we have, right? And it has a theta input also, because you need to have the theta, sine theta, cosine theta for all those calculations, right? This is the matrix we calculated in the previous class, last Thursday. So 3 currents coming here, IA, IB, IC, right? And 3 currents extensive here, right? They're going to come here. We convert them to, this is the ID and this is the IQ, right? We get the actual value for ID and IQ, right? I know how much they are my reference. I want to have 10 amps. I want to have, as I said, for the unity power factor 0 amps, right? These are the desired value. These are the actual value. How did I calculate it? I measured my current in my circuits, right? Convert them to the DQ, and now I know how much is my DQ. See, I'm not putting the O there, you know, because O, if the system is balanced, O is going to be 0. Now, if you know a little bit about the control, what do we call this one? If I know basic of control, it is not that much. We call this one error signal, right? This is desire, this is the actual, right? The difference between desire and actual is the error, right? We have an error signal here, we have an error signal here. I'm not sure how many of you guys have any course in control, basic control. So you can use in this course, we use a PI controller. PI is a proportional plus integral, right? I'll talk about the PI. What's the PI control? There is a math function for that part, you know, what it is. So this two output of this one is going to give me ideal value of EDEQ. So how I can control the power and current. Here is not under my control, right? I cannot do anything. This one they are fixed, right? The only thing that I can control is I can control this voltage, right? Which with my inverter. See, I can change MA, I can shift it right, left, right. These are what I can do. You know, you experience that one in the phase one. As it go 90 degree ahead or 90 degree back, right? So I can shift it back and forth. You know, I can change my MA. In the phase one, you couldn't do that one because it was 6-step inverter. You don't have control of that one. You just go like a half a VDC and VDC. No, sorry. 1/3 of the VDC and 2/3 of the VDC, right? But when it's a sine PWM, we have a modulation index, right? Module MA. I can change MA. If I can change MA, I can change my output voltage, the fundamental, right? So the only thing I can control is this value, or equivalent value of them in the DQ, right? I have an EA, EB, EC. I'm going to have EB, EQ, right? This loop is telling me, hey, if you want to have this much current, you should have this much EB. Voltage, not error rate. This E is standard. Because I use a V here, I use E here.
Okay.
Yeah, that's the reason I use that. Now, the next phase what we do here, we are going to prioritize this one. I'm not going to VDC or VDC over to check this one. I think it's a VDC, but I need to check. We divide this thing, these two value by VDC, normalized. Now I have these two signals. See, these are the power signal. Hey, you see, you should have this much voltage here to be able to have that current. But for my control, remember, how much was the peak for here? Maximum linear modulation. Anything ring in your brain? One, was it one, right? Like 1 degree, not that old, you know. And you guys are young, you should be have a better memory. You say the maximum of MA, how much is it? 1, right? You say it's 1. So this is a power signal, you know. It's going to be like equivalent to 480 volts, something like that. Those kind. I divide by VDC to normalize the thing. Now, these two are going to come here, and now we have a DQO to ABC. And again, we need theta here. Every time we are doing this transformation, we need a theta, right? Now you can see how important is the PLL. What we are not going to talk about, but how important, because PLL is going to give us the theta, is going to give us the V here, right? To calculate all these things. Now, here, let me call it, this one I call it MQMB. Like M, I call modulation index, right? M was a modulation index. I call this one MQMB. This one is going to give me 3 outputs. It's going to be MA, MB, MC. What I do here, because I said I don't want to go over 1, right? I'll say, put a limiter here. Limiter here. How much is the limit, maximum, minimum of this one? Why? I don't want my modulation index goes more than 1 or less than 1, right? I put a limiter of plus minus 1. These are the limits. If it's between minus and plus 1, whatever it is, pass it through, right? For example, because this MA is going to be changing, right? This MA is going to be a signal like this. For example, here is 0.2, pass it through. Let's say MA is like this, right? You said, okay, hey, here you are going back. No, I want this signal. Send me this signal. Cut it here, you know? Yes, part of it is going to be sine, but it's going to clamp here, right? Because it's going more than 1, right? So what this part does, if this signal, they are less than, absolute value of this signal is less than 1, they are going to exactly go through this one, no change. Here and here is going to be the same. But if somehow they are going to go more than 1 or less than 1, it's going to clamp them, right? It's going to keep it there. Yeah. And now, the next part. Actually, okay, that's fine. The next part, what do we do with the sine PW to get my switching signals? I compared it with a triangular waveform, right? So I put this one here. I put a comparator here. And here, VTRI, okay? I'll put a triangular waveform here. Make sure, what's this triangular, you know? When you do this one, make sure it's like this.
So,
You're gonna set in your simulation. This one is maximum 1, minimum -1, and the frequency is based on whatever we say, 10 kilohertz switching frequency, 5 kilohertz switching frequency. Whatever frequency we say is the switching, you select the frequency for this wave. Right.
Why is it we always use the triangle wave? Why not?
You can use the sawtooth if you want, you can use this one. Or you can use down, you can go with this one.
Did you use a sine wave?
No, it has to be a carrier waveform, no, it cannot be sine. This one. You know, remember, we went through this one, why we use the sine carrier. I derived the equation, you know, see how much is going to be output voltage. If you use this one with a sine waveform, you're going to get 0.612 MAVD, remember? VDC, we say that that's a fundamental of the first harmonic. If you use a sine waveform, I don't know what's going to be. Remember how did we do it? We say, okay, we have a control waveform, and we have this one, right? And we say this one is kind of constant. I went through those similar triangles, and I proved it, right? But if this one is like this, I don't know. See if you can go try it, you know, that's a good thing. I don't think so you're going to end up with a good thing, but see, maybe you get a better harmonic system. I don't think so, because if it was people, they have done it about it. But I'm saying, use this one, you know, see what you're going to end up, you know, calculate those things. Now, what are these things? Output here. Is it comparable, right? If that one is more than this one, is high. If it's less than this one, is low, right? 1, 0, 1, 0, 1, 0. Is different, right? So basically, this one is going to be SA. This one is going to be SA plus, let's call it, or up, I don't know. Remember, we have a leg, whatever you want to call it. You can call it up, low, or you can say plus minus. This one is connected to the positive bus, this one is connected to the negative, but they call it different name. You know? I put a plus minus, okay? SA plus means this switch. SA minus means this switch. So this one is SA plus, this one is SB plus, and this one is SC plus, right? And how about the SA negative?
The opposite.
Right? This is the SA negative, SB negative, SC negative. Right? So what is going to happen to these signals? See, this is the control box. Let me put it here. This is all in the control system. This is all in the control system here. So those ones are going to come out here and go to this inverter, the power cell. This is the control. Okay, now I need to talk about the PI. What's the PI? But is it clear? This is what you are going to do for your. This is one of the most critical part of your project. You know, you are going to do that. You are going to work a little bit more on the math, but this is the basic. We can do this one, but I want to ask you. I'm going to ask you to do what I'm going to teach you next. You know, but it's very, very similar to this one.
So when we go left to the right, all we do is just generate a switching pattern, right?
Yeah. But
The
how?
objects.
But how to do it? You have to go through this one. Yes.
Okay.
You're creating a switching pattern for the inverter. How to switch turn on, turn off. That's what you're doing. Now, any question? Because you're very good. You don't ask questions from Arnold. You don't ask questions from me. You're very good. But really, this one is clear or not? Did you guys got the concept? You know what you are doing? See, for example, I want to go there, right? Just let's think about the feedback system. Hey, I want to go stand next to that table. What I'm going to do? I start to walk. This is my reference over there. This is my reference. That location is my reference. I start to go. I take one step, and my eyes are feedback. They're the sensor. Oh, you are not there. Go. I'm going there. I'm going there. I'm going there. I'm going there. Hey, you are there. Stop there. You know, this is the control system. You got the control system. Don't go anymore. If somehow my eyes are not functioning well, so I may pass. You know, I may not go there. You know, no, I'm not saying for lab. This is a kind of simple example. You know. My point is, you know, the control system always is watching you. The control loop is always, this is a control loop. Look at here, this is my reference, I went to here, I send this signal to my inverter, right? And I send the current, I bring them back here, right? Look at, this is the loop. I send my reference here, I went through my control loop, I calculated my switching function, I put it on my inverter, right? And when I have my inverter, I say, hey, let me know where I am. Give me my signal. I'm sending my actual current here, and this controller is looking at it. Hey, where you are. If I'm perfect, how much is this error? Zero, right? If you have a good controller, if you have a good eye, it tells you, hey, stand here. If you have a bad eye, maybe you go to 10 meter off, or this way or that, right? So this is, you can see how much is important to design the controller. These are PI controller. Now what's the PI controller? Let's look at what is the PI controller. Hopefully this part is clear, is it? What we are doing. Just I want to understand the concept first, what you are going to do, and after that you are going to go work on the simulation and all those kind of things. You need to know what you are going to do in the system first, what you are working on. That's very important. And after that, hopefully you find a way to get there. Now, what's the PI controller? What is the P controller? They call it proportional controller, right? P. What's a proportional? It's a constant number, right? You have two signals. For example, X, Y, coming here, plus minus. And this K is a constant number. And here is error, right? So this one is going to be K times error. Right? This is a proportional controller is very simple, very, very simple. It's just a constant number. But you have to select the right number. Oh, that's very critical, how to select the number. I'll teach you how to select for this system. We are going to go to root locus and the body plot and those kind of things to select this number. But let's first understand what is this one. How many of you didn't have a control course? Please raise the higher. No control course at all?
Taking it right now.
No, that's good. Those ones they're taking right now, they're not counting. You know, how many of you didn't have at all control course? No, I'm saying this quarter, if you have it, I don't count you that way. You know, if you have the course, you are good. So, no control course. I suggest you definitely take control courses. As an electrical engineer, it's good to know about control. You know, it's weird, you know, to be a control. As I said, it's weird to not to know what's a three-phase system for a basic, you know, 4-year graduate electrical engineer. To not know what's the three-phase system. It's weird to not know what's the control system. You know, basic. I'm not saying to be control engineer, but control. You know, I don't know what they call it here. They call it control automatic. I don't know, control system. I don't know what they call it. You know, take that course for sure. But you have to work a little bit on this one yourself. Now, what's the I controller? So this one was a constant number, K, right? The constant number. I controller is the integrator. It does integrate the error. So basically you have the X and Y coming again. You have an error signal. This one is going to go through 1 over S, right? 1 over S is a Laplace transform of
An integrator.
integrator, right? You know that. So in the Laplace transform, we use a Laplace transform to show this plot. So basically this is the output. The good things about the integrators, they drive the error to 0. That's the good thing about the integrator controller. Because we want to have the error 0, right? Ideally, we would like to have a 0 error. Never whenever we are going to get there, we are going to have always a small error. But that's fine, if it's small, it's okay. But the good thing is the integrator, they force the system to go toward that way to make the error 0. Now, what is the PI controller? And they can have a gain also for this one also. This one could have a gain, you know, right? K gain is time. So PI controller is like this. I have an X, Y, and now I have my error signal, right? Error. This one is going to go through as KP. I'm saying K is a constant number. P is for proportional. Just I want to make sure show you this is a proportional part. I time my error by KP, right? Now, the same signal is going to go through a Ki over S. Ki is the gain of the integrator, another constant number. But 1 over S is the integrator, right? So the result this is my answer. So basically, this block you are seeing here, right? What it does? This one is coming here. It times it by Kp. It times it by Ki over S. Add them together, give you one signal. Right? Clear?
What does that represent? Like that adding it together?
You build it in your now if you use PCM, you have the PI already built in. You can use it. But my time when I was doing my master degree, we wrote all the C code and we do this one. You say you subtract this one from this one, for example here. You subtract this one from this one, right? Time it by KB, time it by Ki over S, and add them together. This is my PI. I did my PI on myself. You know, don't think the PI is a kind of, you know, this kind of a strange thing they are doing in this block. Just they write this equation here. They do digital, you know. I don't want to get to the digital implementation of this one, but you have to do digital because whenever you have a simulation, there's a timer step, means you are doing step by step by step, right? You have to digitize it, you know, but I don't want to talk about it. Okay.
So for the PI controller, does that mean that this is a positive feedback system?
No, this is no. See, this part is called PI.
Okay.
No, this is not positive feedback.
So why is positive?
Oh, here, no, sorry, here is
Okay.
negative. But it doesn't matter, you know, you can put positive here, but us is negative, usually it's negative. Yeah, but still you can use the PI and add them together, you know what I'm saying? But yes, usually this one is negative. Any question on this part? Because I want to talk about another type of PI and finish it. You can start to focus on your project from here even, you know, but I'm going to work a little bit more on it. Now, what you guys you need to do, can somebody tell me what, when I give you this project, what you should do? What part is the most important part for you guys to do?
Understand.
No, now I assume you understand that part. You passed that paper. Now you understand what you are doing. What the control? What do you mean by control?
We want charge of this charge.
No, that one is the concept of what you're going to do. You know, that one you're going to set the numbers here, right? You put a 10 or minus 10, you know, each charge of this charge. Is there anything else here? And these ones, they are all known. You know this matrix, you know the theta, you calculate this thing. Do you know the value here or not?
No.
These are the part you have to determine the right value for this one. When you simulate this one, I'll do some simulation. For example, you put IQ ref this much, right? I'm sure you're going to start with something like this. Even you cannot see this one because you're going to be off. You know, your IQ is going to go really off because you're not doing a good control. Because your numbers are really bad. But hopefully one day you get to this one. You do your IQ ref and you see your IQ is going to go like this. And you say, hey, I want to change my IQ ref to this value. This is the reference value. Reference value is under your control. You can do whatever you want, you know. And IQ is going to again pick up from here. Right? This is a good control system. You change your reference value, your actual value is going to follow the reference value, right? If you're a good leader, other people, they're going to follow you, right? If you're a bad leader, you say something and the rest, they do whatever they want. That's like a good control system, a bad control system. Here, if you're a good leader, you say something and the rest, they're going to come follow you. Hey, yes, you are good. No, let's go down. So you have to find out how much are these KPKI. They call it control design. Control design of this system.
What about the delay in doing?
Delay for what?
Let's
That
say
one?
Yeah.
Every system has a delay. This part you mean?
No, the second.
This part you mean?
Yes.
You're sitting in your car, right? You start. You want to go to 60 miles. Can you jump 60 miles? You start to push the gas pedal, right? And you're going to start to speed up. And you look at the kilometer, right? Or mile meter, you know? And you see 60. When you get to 60, you pull back, right? And keep it. You cannot jump. Every system has an inertia. What's the inertia in this system? Inductors. In the electrical system, inductors, they're like an inertia in the mechanical system, right? So this is delay. I cannot jump my current to that value.
I mean,
But we can make it the faster, the better. They say the control performance is better, right? That's what it is.
Yeah, that's what I was trying to ask. How to minimize that delay?
That's a good control design. You will talk, if you have a control course, they call it critical damping. Some of you have control, maybe they call it critical damping. You could have an under damp system, you could have an over damp, and you could have critical damping, right? For those one, just to say what it is, for example, this is our reference value. If your system is under damp, I think this is under damp. This is your reference. This one is going to go slowly, it's going to go there. It's going to go get there. If your system is over damp, you're going to go like this.
I think that's under there.
I don't know. One of them is under, one of them is over. And if you design it for critical damping, that's what I want you guys to do. You're going to go like this. Boom. All of them, they did the same thing. But this guy went fast. Basically, this is the fastest possible. You cannot go faster than this.
What components can show that? Which components in the circuit can show that critical damping?
KPKI. KPKI. That's what you need to calculate. We'll get a little bit more. Let me hold on. We'll get a little bit more. There, I'll tell you how to do that. Not how to do it exactly. You have to do it, but I'll show you the way to go through that path. Any question here? If you see about the different controller, they say adaptive controller, neural network, I don't know, fuzzy control, those kind of, all of them, they are trying to do the best control, the fastest possible to get there. That's the different control methods. For this case, I'm saying, but they do the advanced topic, but this is a very simple topic. PI is going to work pretty well here. Now, we're done with this part. Oh, PI, type of PI. So what is PI? So basically the transfer function for this PI, we call it a transfer function. PI. It's going to be KP plus KI over S, right? You have a signal coming, goes to the PI, X, Y. Basically, it's going to time X by this PI, right? That's what the PI. There is another formula for the PI. In PSIM is using that one, I'm saying it, and I like it better. In the PSIM, they use it this way. It says the transfer function is Kp times 1 over tau. See, 1 over S is still this. Time this one. What is this one? It's going to be Kp plus Kp over tau over S, right? So basically Kp, if you are going to go with these two models, Kp is Kp, right? Yes. And this one is what? Ki, right? I like this model. Why? This is kind of time constant of the PI. Time constant of the PI. For your simulation later on, you're going to start, use 1 millisecond for this one. 1 millisecond means 0.001 in your model. 001. When you are doing your modeling, you put a point 001. Later on, you're going to get to here. Right now, maybe you're a little confused what he's talking about, but when you get to that phase, you're going to do that. Maybe you can start with some numbers, general. You have to work. Maybe 2, I don't know, something like that. You have to go try. It depends on the inductor value. Here, what we have, switching frequency, those kind of things. But you can start for this one. If you're going to start blindly, without any control design, you can start this one.
So we have to change the value to find the.
You, for example, keep the tau point 1 millisecond, and start to see. Do you see this one? No. For example, go a little bit over with the K. Get worse.
So there is
Bring
no
it
way
down,
to
down.
calculate the.
This is a try and error. This is what we are doing, try and error. We go a little bit up, a little bit down to get it where it is. Experience is very important. Now, if I want to simulate this one, I do it in 5 minutes, because I have done this one a million of times. But for you guys, the first time it's going to take you time. Maybe you get frustrated. You don't know. You say it doesn't converge. This problem doesn't work. No, it has a result. I'm sure there is a result for that. But PSM has this type of PI in small. It uses this one. Click on it, and help. You can see this one. This is there. So we finished this part. Now, any question here? We are going to get heavily involved with the math now. Any question?
Is that a range of the KP? Is that a maximum range?
No, you have to use a design. This is design. You design the system. We'll get to the design part. I explained. I was thinking. I thought I'm going to finish that one, but it's like no, I'm not going to get there. But I'll tell you how you get a transfer function for the system. And after that, you can do the root lookup for the multi-plot or something like that to select this KPI value. You plot those on and you see where you are, and you can do this. Now, I'm going to go back to the system. Right now, no control. I don't know how far we can go. Remember here, we had a P is 3 over 2 IQ ref times V. The other one was minus 3 over 2 V ID ref. What I like, then I change my P ref in the system. Here, when I change my reference value, I'm changing my P, right? I don't want my Q get affected. Basically, they will be independent of each other, right? But if we simulate this system, you can see when you change your P ref, your Q is going to also change. And they are kind of coupled together. They are coupled together. When you change this one is going to start to oscillate. It's going to get there. Again, it's going to get kind of tuned. But there is some transient. When you change this one, we are going to talk about the decoupled control of active and reactive power. Decoupled means when I change my P, hopefully my Q doesn't change. So by Q I mean reactive power. When I change my reactive power, hopefully my P doesn't change, it stays over. We call it decoupled control of active reactive power. The same circuit, keep in mind. We call it decoupled control of some people they call it vector control. Some people they call it vector control. Usually is used for the AC motor control, like synchronous machine and induction machines. But because it's very similar, you don't know about that, but it's very similar to that one. They call this one also vector control. If you hear about the vector control of the inverter, it's the same thing. Decoupled control of active reactive power. Some people they call it vector control. Now let's start from here. Forget this part. I have the inverter EA, EB, EC. Let's write the KVL equation here. It's going to be EA is going to be, the current is going this way, right? It's going to be VA plus RIA plus L DIA over DT, right? And EB is going to be VB plus RIB plus LDID over DT, right? And EC is going to be VC plus RIC plus LDIC over DT, right? Okay, one here, and one here. Right? Let's put it in the matrix form. Let's change it to the matrix form. It's going to be EA, EB, EC is going to be VA, VB, VC plus R 0, 0, 0, R 0, 0, 0, R IA, IB, IC plus L 0, 0, 0, L 0, 0, 0, L times D over dt at IA, IB, IC. Correct? Is it correct? Just I need to remind you a little bit of from what we had from last class. Somebody, send me an email for Tuesday class. I'll bring the inverter and control, but what I put here, you can see a real system, Someone sent me an email like around 3:30, not later than 3, tell me, bring the word you want to, you guys can see the system. It's going to be a little bit heavy, but it's an open inverter, you can see what's inside the inverter. What we did, if you remember, we said FDQO is CFABC, right? And you remember, what was the FDQO? It was FD, FQ, FO. FABC was FA, FB, FC, right? You can remember those things, right? And we said C minus, what was C minus? Inverse matrix of this. And C was, I think it was the cosine, 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 sine, 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 1 over square root 2, 1 over square root 2, 1 over square root 2, times 3 over 2 everything, right? You had this matrix from the last class. Now, we said C minus is 3 over 2, C transpose, we had that one. So keep this in mind, Now let's go back over that. I want to move all my equation from ABC to the DQ system. My goal is to derive new blood diagram. We went through one blood diagram, right? For control. I want to give you a little bit more advanced blood diagram of what we need, something with a better control, better tuning on the system. But we have to have the equation for this system first to get the DQ equation, equivalent DQ equation for this system. I'll give you one homework, I'll work on it. Just I'm going to give you like an RLC circuit. This is mostly like electric machinery, But I'll give you a 3-phase RLC circuit, and I'll ask you to find the DQ model for that one. And you can see it's fun, look at it and see how much it's going to be different, You have a regular ABC system, you bring it to the DQ to see how much change you're going to see, how much it's going to make it easier, I'll give you that one, for over the weekend, you can work on the second homework. But now, what should I do? I want to convert everything to DQ, right? How about if I times everything? These are metrics, be careful. It's very important you time it from left or right. These are metrics now, right? How about if I time everything from left to C, right? It's going to be C times EA, EB, EC, right? What is the C times EA, EB, EC? It's going to be EBQ, right? I mean E. Just I'm going to now summarize this one this way and write that one. I'm going to put it this way. E, A, B, C. E, A, B, C means this. I don't want to write everything again, general like matrix one, right? So that one is going to be V, A, B, C. These are matrix, you know, these are matrix, right? This matrix here, V, A, B, C, E, A, B, C, plus, basically I should have done this one with a small r. I should have put a small r here and here called the matrix R. You know what I'm saying? Let's do it this way, maybe we don't get confused. Make this one R, R, R. So here is the R, R, R. Right? So this big R, if you understand, you don't have to change it, you know. That's why I said this, keep it R, whatever I wrote, you know. But this R is a matrix, 3 by 3 matrix. This is R, see? This is the matrix R. This is a VABC. Let's play this. This is the EABC. This is the IABC. This is matrix L. And this is again IABC. Right? So you don't have to change the R, you can write it this way. So basically it's going to be R, IABC, right? Plus L, D over dt, IABC. Right? I want to change everything to the DQ. I times everything from the left times by C, right? So if I do that one, it's going to be C EABC, and C is that transformation matrix we had from last class, equal to C BABC plus CR IABC plus CL D over dt, right, IABC. So what is this? EDQO. This is a EDQO. What does it mean? I'm going to write only this one. It means this one is equal to what? ED, EQ, EQ. These are the output voltage of the inverter, right? These are the output voltage of inverter in the DQ system. In the DQ system, right? What is the CVABC? It's going to be VDQ. If later on we're going to talk about this, but if I select my voltage to be aligned with the Q axis, select to be aligned with the Q axis. I'm not going to do it now. What is going to happen? How much is this one? It's going to be 0 VU, right? Because VD is going to be 0, right? VQ is going to be V, and VO is 0, right? But forget it for now. Let's not think about it. Right now, basically, it's going to be VD, VQ, VO, right? Now, let's think about this one. Can someone tell me what is this? Huh? If it was CIABC, yes, I can say it was IDQ. But it's C times R times IABC.
You can divide R out. R is a scalar, it becomes an identity matrix.
If you look at R, look at here, is the R times identity matrix, right? Right? So basically this one, I'm going to just do it quickly here. That R is equal to R means the value, not matrix anymore, right? Times I3 by 3, right? Times I3 by 3. So this R is a number, not matrix anymore, right? This is not anymore matrix. So C times I3 by 3, what is that? So basically it's going to be C, you see here? It's going to be C times R value, a scalar value, not matrix, times I3 by 3 times IABC, right? This R is a scalar, I can bring it to the left, right? I can move it around now. C times I 3 by 3 is C, right? C times IABC, IDQ. So basically, I want to keep it in a matrix form. So basically, when I have I, so I have A times I, let's put it this way better. This one is equal to I times A, right? In the matrices, you cannot, exchange the places, right? A times B is not equal to B times A. You know that, right? For sure you know this one. A times B is not equal to B times A. Maybe, by chance will be, but in general is not, right? You know that. But if B is I, you can replace them, right? You can say A times I is equal to I times A, right? Maybe this way is a little easier to understand. So this one is R times I 3 by 3, right? R is a scalar, put it there. C times I 3 by 3 is equal to I 3 by 3 times C, right? So basically this one is going to be, let me write it. C times, I put the R value here, I 3 by 3 times I ABC. Right? Next, I'm going to bring this R here, and I'm going to bring this I 3 by 3 also here. So it's going to be R, I 3 by 3 times C. See, I exchanged the places of these two. Times IABC. How much is this one? IDQO, right? So this one is going to be IDQO. How about this one? Is going to be R, the big matrix, right? This is R, right? So this one was EDQO, this one is a VDQO, this one is R, IDQO. This one is going to take lots of time to calculate. This one is going to take a lot of time. Let me see how much I can do here, and we'll stop. I'll go a little bit, and I don't think I can finish that one. C is a transformation matrix. L, again, what is L? Let's work on it first. I want to work on how did I write it here? I said, yeah. I'm going to work on this one. C. I have C L D over dt IABC. Right? This is the last term I need to calculate. What is L? Again, L. This one is L times I 3 by 3, right? Right? I can switch these two, right? I can put it L. L is the matrix. L is the matrix, right? This one is L times I 3 by 3 times C times D over dt IABC. Now this one, I need to calculate this part. This is clear. This is simple. Now I need to calculate C times IABC. So let me see how they do it here. D over dt IABC. Let's see how they do this work. Oh, okay, got it. I have like 5 more minutes on it. Let's work on this part. So for now, keep this part here. I have an LC here, right? I want to work on this part first. D over dt IABC, right? What I can use instead of IABC? I can put C minus IDQO, right? Can I? Can I write this one this way? D over dt C minus IDQO. Is it correct?
Yes.
Right? So now I want to, these are both metrics, right? If I want to calculate the d over dt of this one, it's going to be d over dt C minus times IDQO, right, plus C minus times d over dt IDQO, right? Derivation of this one times this plus derivation this one times derivation of this one. You know, the direction is good. I cannot put C minus on that side. You know, be careful. Now, so this one is good. I don't need to do anything about this. This is good. The one is kind of a little bit tricky to calculate here. Let me write this equation and I will stop here. So we got here, let me write here what I have. I have a EDQO. I'm going to stop here. Just I want to read because I can take it from here next time. Is equal to VDQO plus R IDQO, right, plus. How about this one? We got here, right? It's going to be LC times this plus LC times this, right? So I'm going to write it here. Plus LC, let's do it here. LC, see, this two I say that Y we can change it, right? And how much was the D and LC times? Let's write it here, you know, a little bit more clear. D over dt, IABC, right? And we said IABC is going to be C minus IDQ, right? Right? Is equal to over there. And I said this part, right? I'm rewriting what I said over there. It's going to be D over dt, C minus, right? Times IDQO plus C minus times D over dt IDQO. Right? Now let's time this one. Now it's a little bit more clear. This is the last one. I'm going to write here and stop it. EDQO is going to be V DQO plus R IDQO. See, this is a R, this is a now plus. Now, let's time this one. It's going to be LC, it's going to be L times C times D over dt C minus, right, times IDQO. Next week, I'm going to work on this one to calculate this part. What is this one? Because this one is good. We know what is this one, right? This is simple. And this one we know what it is, but this one I need to calculate. Plus, how much? LC times this one, right? LC, C minus, see, LC times C minus times DQO, D over dt, IDQO. How much is this one?
1.
Not 1, I. Is I. I 3 by 3, right?
Yes.
And I 3 by 3 times L
Yeah.
is L. So basically it's L D over dt IDQO. We need to work on this term. We need to calculate this term, and we have the DQ model for it. And I'll leave it for the next class. So next class, I'm going to pick up from here. Just if I calculate this part, I'm done. I have my model for the DQ system. Bring your homework, please. And Arno again is here. He sent an email to the class. If you have a question, ask him for help. You know, he can help you a lot, you know, on the project.